Thank you. Thank you for the introduction. So, first of all, I would like to thank the chairs of this session for allowing this presentation, which is not in the program. In particular, Professor Mas from Seoul SMT, where I am at the moment staying for my Fulbright sabbatical. So I'm sharing some research, a brief overview of preliminary work we've been working on concerning textile reinforced mortar, textile reinforced concrete, which is applied in actual retrofit of a historic industrial heritage structure. So there is a context to this. Basically, it ties in with a point with Professor Myers just mentioned concerning historic structures, but different type of historic structures. This was considered as industrial heritage, a reinforced concrete industrial heritage, and because of the conservation and values in conservation of the reinforced concrete heritage, it was decided to consider specific options. Not anything can go. So an FRP traditional solution we are using normally in actual interventions when it comes to the carbon fiber composite was excluded by the competent authorities, and we had to find an alternative solution for the retrofit, which was in line with introducing a cement-based intervention. And because of the research conducted at the time, we were looking at a self-healing composite material with crystalline mixtures, which was then developed into a textile reinforced mortar of a certain high strength, applied as a strengthening to the structure. As part of the conservation approach, it was also decided by the research team to reinstate the structure and put it back into operation. So this is a 90-year-old structure, which has to once again contain 400 cubic meters of water, and therefore to perform an actual use through an adaptive reuse for actual use in the longer term as an asset. So getting an industrial heritage again to perform. So that is the context. And in this situation, we have therefore a structure which is on the sea. We are in the context of our island states. It's a small European state in the middle of the Mediterranean. So we are still in the region, Italy, South Italy. But our country is small and it is much exposed to a coastal environment. So the structure is literally about 90 meters actually from the shoreline. That is why it is heavily degraded, as you can see in the picture here. So this is the context why we went on to develop a textile reinforced concrete. I would also like to mention that this is in the context of the development of this textile reinforced concrete and ultra-high durability, ultra-high performance concrete within the framework of a European Horizon project, which we were partners in, and where we developed a UHPC and the textile reinforced concrete with self-healing properties for new interventions, floating textile reinforced structures, which we developed, but also textile reinforced concrete for application on historic existing structures. So this is the final stage of our program, where we eventually validated our work by filling in this tank with water to assess the performance of the TRC as applied. But before all that, we had to go through different stages to first identify the right solution and go on to see how it performs in actual circumstances. Well, this opened up quite a lot of activities which are still ongoing. So that is why I said this is preliminary work which is in progress. In the first stage, we looked at how to first identify the right solution, because some solutions on the market we tried, we were happy to use, but presented some challenges because the textile couldn't really be flexible enough to be applied on a curved structure with double curvature. So this, to be honest, presented for us quite a challenge, because we got really nice solutions, but were not practical for us. So we went on to a second stage where we proposed to get the textile reinforced material, which we designed, get it produced, shipped over, and then we applied the textile, the resin to the textile on site in a purposely created space where we could control the environment because of practical reasons, and then apply it when it's still, let's say, flexible enough to apply it on the complex geometries of this, the double curvature and so on of the structure. And this therefore necessitated that we assess certain issues. For example, applying a textile reinforced concrete which is with a hardened resin or with a fresh resin in the mortar. So this created some innovation which we were looking into. A fresh impregnation of the resin and then integrating it in a fresh mortar. But also we were concerned with the exposure temperature in real circumstances. So signing off such a structure to operate with that flow, the water pressure, required us also to guarantee performance over a number of years. So what happens when you have exposure to consistently high temperatures in summer, so we are talking about 60 degrees Celsius or even higher in the concrete, and the textile is just 8 millimeters below the surface. So what happens when you have this exposure sustained over time? So we decided to focus in the second stage on assessment of the textile reinforced mortar to higher temperature, both in curing conditions, but also during the test itself. Eventually, we applied the textile to this test. So I will go rapidly through the work. It's a summary. So in stage one, as I said, we went to assess different options. So we looked at two commercial options. One is a textile which is impregnated with a styrene butadiene and the other epoxy resin. So here I'm referring to two particular solutions out of a number we assessed. I'm presenting the high strength mix we used as well within the framework of the Horizon 2020 project, with the self-healing intention as well. But I have to say that the purpose was to have, let's say, a similar type of textile from different sources, one with relatively rigid configuration and the other one also rigid, pre-impregnated, but with laminated filaments. So first we had tests concerning the flexural behavior of the assembly, which, as I said, consists of 16, 18 millimeter thick textile reinforced material with the textile. And these are some of the flexural tests, which already started giving us an indication where a certain curvature could be achieved with the epoxy coated textile carbon fiber, whereas with the styrene butadiene we started getting immediate failure. On the other hand, when it comes to tensile tests, we were noting different behavior in the samples, which are better perhaps explained in the graphs, but it was obvious that there was a higher strength which was initially achieved with the indirect tension, with the epoxy coated samples, and lower strength with the styrene butadiene. But I have to say that in the first case there was less recovery upon first failure of the samples, which is perhaps to be expected. So we had a higher strength, but then less recovery as there was progressive failure of the samples. And this could be explained also by the typical three-stage approach when we assess the behavior of such textile reinforced mortars. So, in conclusion, we also looked at the overall toughness of the material, and we also noted that if we want the toughness, there was a certain degree of improved performance when it comes to the styrene butadiene. This was attributed to the bond of the layers. And in fact, there are other ongoing studies which concern the bond between the cement mortar and the textile assembly. So in conclusion of the first stage, we came up with the decision to look at, when we are comparing the same text width and with the same rough spacing, where we were looking at solutions which would guarantee a higher strength in our circumstances, and we decided then to move on to the second stage, which very quickly looked at, as I said, the environmental exposure. How would the system perform through environmental exposure? So basically we looked, as I mentioned, at temperature exposure is the main key element. We have ongoing tests where we are seeing what happens in a salt environment, because we know that there is an improvement actually in performance when it comes to some crystallization of salt at the interface. But that's another study. So we looked at tensile tests this time round, And we applied, as I said, the textile assembly either hardened, impregnated samples in a mortar, or as fresh impregnation, where you have the textile which is still fresh in the mortar assembly. And we compared the two. For the purpose of quality control in actual application, we also looked at poorly impregnated samples or with no impregnation. So we could see what we are risking if we get issues on site. As I mentioned, we looked at exposure at 60 degrees Celsius, and we used this machine also to assess with high temperatures during the test itself. So we set 60 degrees in this case of the preliminary first stage. And the results indicated a similar performance. So there was some variation between samples which were fresh impregnated or which were pre-impregnated. However, we could not observe significantly drastic changes. However, the quality of impregnation, of course, as expected, does make a difference. So the fact that you have improved impregnation of samples, adequate impregnation, is key. So these are some of the results compared to reference sample. However, I must say that at 60 degrees Celsius, there was indeed a reduction in performance. This was very evident repeatedly in our tests, as you can see here. So we had also curing in water and curing in air, also to see the realistic situation of our structure, which is with a structure actually not cured in water, of course, it's area structure, as against water curing in ideal or improved situations. But the main difference was the temperature, where it was obvious that at 60 degrees Celsius there was indeed a decrease in performance of our specimen. And this conclusion led us also to take precautions and some considerations when it comes to our structural design, the structural design for intervention in the structure. So, as I mentioned, the key objective, and this is our phase 3, in conclusion, is the actual application on the structure. So, the structural solutions were the development of self-healing ultra-high performance concrete, which we used as jacketing to our columns, and the textile reinforced concrete, which was used as a confinement to the tank. We started off by creating replica structures, real-life, real-size replica walls, which we created on-site, in site conditions, to see the operation, the application, and also the actual, we tested some of them. That's the purpose of another presentation. But then it was all about applying this in the real structure. As you can see here, working at night also, because we had significant problems of shrinkage, so we had to deal with that. I must say we had also some problems at the interface, and that is another study we are looking into, the interface between an existing concrete and the new application. But this is the end result. So how would we validate the solution? We validated it by filling the tank with water and then emptying it. And we integrated many sensors in the structure. We have full sensing, to strain gauges, to see exactly what's happening within the original structure, which was repaired and restored, of course, and also the textile application, textile reinforced mortar application on the surface and at the interface. One defect we experienced, for example, in real application was some gaps which we had to fill in with epoxy injection. We identified these through ultrasonic and acoustic emission techniques. So that is another realistic scenario we have to deal with, which we are also studying. But the end result could be validated. So we validated the structure. We filled it twice initially to see that it works. And the result gave significant, let's say, benefits in operation. The stresses were aligned with our predictions and our finite element models. Thank you very much.
Thank you, Ruben. We have some time for questions. Anybody question? I'll start with one real quick, and then we'll jump to you. So you showed the load test of the tank filled and unfilled, and I'm curious, is there any creep effects, perhaps, on that type of grid system, or can you provide a little bit more detail about the fabric or the grid that was used, and if there's any creep sensitivity to sustained loads, let's say? Because you looked at temperature and
our modeling of the structure was referring to the original structure, a reinforced concrete tank. Typically, the structures you have the reinforcement for hoop stresses in the center of the section. It was a 15 centimeter tank overall, 15 meters high, and we designed for that. So we assessed how it would have been designed in the 1920s, 30s when it was first constructed, and we could see how optimized or otherwise it was. Then we introduced in our model the textile reinforcement, and this was, from a structural perspective, the first headache to exactly see what's really happening in the composite section. So in reality, how are stresses transferred, if at all, to the textile? Where are the stresses going first? They go in the reinforcement. How rigid is the system to ensure that there is a transfer? And to be very clear about this, we are studying this and how it's really happening, because I'm not sure I have a clear feedback to that question. And so creep comes.
Yeah, it looks like you lost significant cross-sectional area.
Yeah. We reinstated that. With a replica concrete.
Well, first of all, many thanks for your presentation. Well, actually, my question was similar to that. Just another curiosity regarding the setup that you use in the tensile test. Because when you basically grip the specimen, since we have temperature, did you use some resin suitable for elevated temperature, or how did you clamp the specimen during those tests in the machine?
So we are talking about 60 degrees Celsius. The specimen, the end textile was bent, and also to ensure that there is no slippage, because in our first test this was crucial. And we clamped with aluminum plates in the grip. Well, the effect of temperature on the clamping mechanism, that is your question. Actually, we did not really look in detail into that.
Okay. And how did you measure the temperature within the specimen? I mean, when you say test at 60 degrees, you mean 60 degrees in the air, 60 degrees within the specimen?
The chamber, this machine is designed purposely. It's a chamber which is sealed and ensure that the temperature is 60 degrees.
So in the specimens, you are not sure that at the center of the specimen you reached 60 degrees?
The specimen had been stored in a chamber 60 degrees throughout, taken out of the chamber at 60 degrees and placed in the machine, and the test was done at 60 degrees.
Okay.
So that was found to ensure that we were validating the test at that temperature.
Okay, thanks a lot.
Hey, how you doing? Anthony with Simpson Strong Tie. Was the strengthening performed on the exterior and interior of the water tank?
On the exterior only.
On the exterior only? Okay. I was going to ask, the only question I had, if it was on the interior, constant water would be a concern about the bonding of it,
On the exterior only.
Gotcha.
Hi, Ruben. Very nice presentation. I mean, the case study of strengthening of the tank is very interesting. One question regarding that strengthening. Do you guys measure crack widths in the tank, given that these kind of structures are really designed for reusability, so to control cracking? I mean, you guys measure before and after to see how effective was the strengthening?
The before state was structure partly collapsed because it had severe spalling, so we couldn't actually do it. So we repaired. We had to reinstate about half of the tank with new reinforcement, which was integrated then in the older structure, and we performed electrochemical chloride extraction and reutilization of the remaining structure, and then we replicated the concrete and modulus to reinstate the missing parts, but we retained as most of the original as possible. Once it was reintegrated as the original structure, we did not fill it because we weren't confident enough to do that. So we use the textile solution to, let's say, have an extra reassurance that we have, and it was over-designed, I have to say, to ensure that it can take the stresses as if the reinforced structure is not there. At the moment, we are trying to understand what is the interaction between two such structures together. It's something which is work in progress from a structural assessment point of view. We have sensors in the reinforced concrete section on the reinforcement. We have strain sensors, and we have strain sensors also on the external textile reinforced concrete. And we are trying to see the behavior when you fill up and then see of the two. Thank you very much. Thank you.